Welcome to The Explainer. Today, we're diving into the most powerful, mind-bending forces in the entire universe, black holes. But we're not just looking at how they eat stars. No, we're investigating how they might actually delete reality itself. Okay, let's jump right into this cosmic mystery. Because, we all realize black holes are terrifying, right? They're strong enough to rip entire stars into atom-sized pieces. But frankly, the real threat isn't just their brute destructive power. The true danger, the thing that keeps physicists up at night, is that black holes threaten the very fundamental laws of our universe. Section 1. The Cosmic Threat. The Ultimate Threat. So to understand this absolute cosmic crime scene, we first need to understand our suspect. Picture the event horizon of a black hole like a river that abruptly ends in this enormous, terrifying waterfall. As you float along, the stream imperceptibly gets faster and faster, and if you swim just a bit too close to that cosmic waterfall, well, the current pulls you towards certain death. It completely and permanently separates the inside of the black hole from the rest of the universe. Once you cross that point of no return, there's literally no way of telling what's going on inside. But here's the kicker. Black holes don't just sit there forever. Thanks to the brilliant Stephen Hawking, we know they slowly evaporate through a process we call Hawking radiation. Think of it kind of like a hot pot of water on a stove, losing its water as steam. The black hole is constantly losing an extremely tiny amount of its mass, just radiating it away into the freezing void of space. And this brings us to our ticking clock. Just look at the sheer ridiculous scale of this number. It would take a black hole with the mass of our sun 10,000 billion years just to lose 0.0000001% of its mass. It's an almost incomprehensible amount of time. But the point is, in the far, exceedingly far future, black holes will eventually evaporate and completely disappear. And when they finally pop out of existence, they might take something absolutely fundamental with them. Section 2. What exactly is information? The arrangement of particles. Before we can figure out what goes missing when a black hole vanishes, we really need to nail down what information actually means in physics. It's not a tangible thing you can hold. It's just the specific arrangement of identical building blocks. Take carbon atoms, for example. Arrange them one way, and you've got a dusty lump of coal. Arrange those exact same atoms in a slightly different way, and boom, you have a sparkling diamond. Add a few more atoms into the mix, and you could get a banana, or maybe a squirrel. The basic building blocks of literally everything in the universe are exactly the same. They depend entirely on their information to be distinct from one another. Without information, everything in the universe would just be a completely identical mush. So the absolutely crucial point to remember here is that according to quantum mechanics, information is immortal. It is indestructible. It might change shape, sure, but it can never be truly lost. Even if you take a physical piece of paper and burn it down to ash, the atomic history, that underlying information, is technically still there and readable. If you had magic godlike powers and could somehow collect every single carbon atom in that ash and perfectly measure the smoke and the heat radiating from the fire, you could theoretically reconstruct that exact piece of paper. The information is always preserved in the universe. Section 3. The Information Paradox. A serious problem. All right, let's look at this massive clash of the titans. We have a literal paradox staring us right in the face. On one side, we've got quantum mechanics, which relies on information being an absolute, indestructible record that tracks the entire history of the universe. But on the other side, we have black holes, which actively destroy it. By crushing everything down into a singularity, they take completely different things, like our coal and our diamond, and squash them until they are exactly the same. This paradox completely breaks our understanding of reality. Existing, not existing. Without information, everything is entirely relative. This clash forces us to ask the million-dollar question. What the heck does a black hole actually do with all the data it consumes? Where does that information go while the black hole exists? And worse, where does it go when the black hole finally evaporates into nothing? Section 4. 3 possible solutions. Solving the paradox. Physicists have agonized over this and proposed a few wildly different ways to solve this cosmic crime. It really boils down to 3 main avenues of investigation. Number 1, the information is truly deleted and lost forever. Number 2, it's locked away somewhere deeply hidden where we just can't observe it. Or, number 3, it was actually perfectly safe the entire time. Let's break these down, shall we? If we go with option 1, and the information is permanently lost, Well, we basically have to toss out the rule book. We would literally have to nix all our current laws of physics, the very foundation of everything that has worked so brilliantly for us over the last century, and start totally from scratch. And honestly, nobody has a clue what those new laws would even look like, which is frankly a terrifying thought for any scientist. Now, what if it's option two? The information is just hidden. Think of this like having a broken computer hard drive stuffed with all your priceless family photos, but you can never, ever access it again. The data might split off into some weird, inaccessible baby universe. Or maybe the black hole leaves behind a hyperdense information diamond at the very end of its life. Basically, an infinite cosmic clown car crammed with unreachable data. I mean, sure, it's nice to know the data isn't deleted, but if we can't ever access it, it doesn't really help us much, does it? Section 5. Cosmic dirty laundry. Storing information. So what about that third option? The idea that information is actually perfectly safe? Well, theoretical physicists like Jacob Bekenstein and Leonard Susskind figured out something absolutely mind-blowing. Imagine forcefully stuffing your dirty laundry into an overflowing room to create a black hole. You pack in the laundry baskets until the room is completely stacked floor to ceiling, totally maxed out. If you forcefully squeeze just one more sock into that room, it collapses and forms a black hole. But, and here is the really amazing part, instead of filling up the inside of the black hole, throwing more laundry in makes the black hole's surface area expand by one tiny minuscule pixel for every single new bit of information. The information essentially gets painted right onto the outside surface. This means black holes act as the ultimate cosmic hard drive. They swallow massive 3D objects, like entire stars and planets, and encode all of that data entirely on their 2D outer surface. It is exactly like taking a physical 3D paperback book and transferring all its text into a digital e-book. They look completely different in physical space, sure, but the core content, the raw information, is exactly the same. It's just been encoded and memorized in a brand new way. Section 6. A holographic reality. Universe is a hologram. If this theory holds true, that the information is securely painted on the boundary, then that extremely slow Hawking radiation we talked about earlier can eventually learn about this encoded data and gently carry it away safely as the black hole evaporates. Boom, the paradox is resolved. But it leaves us with something called the holographic principle. Think of a real-world hologram, like a 3D photo. It's just a flat piece of plastic that perfectly encodes a three-dimensional image. This principle implies that a person falling into a black hole would experience a totally normal 3D life as they fall. But to an outside observer, they've just been flattened into a 2D image smeared across the event horizon. Now, black holes are obviously extreme environments, but they are still bound by the exact same rules as everything else in nature. So if black holes operate on this crazy 2D, 3D duality, well, it strongly implies that our entire universe might work the exact same way. Since a person inside a black hole wouldn't even realize they were just encoded data on a flat surface, we might be sharing that exact same fate right now. Which leaves us with this final, truly mind-bending thought. Is our 3D reality just a cosmic hologram? Are you, me, and everything we know really just a flattened image stretched over a 2D flat screen at the very edge of the universe?